The last talk of this first session, Peter's going to tell us about making effective string constraint solvers.
Okay, thank you for introduction. I'm Petr Janků, and I'm a PhD student at University of Brno University of Technology. So I would like to start with motivation. Why analyze string programs? Strings are fundamental data type in many programming languages. String manipulation are often difficult to reason about automatically and could easily lead to unexpected errors. Some of these errors could have serious security consequences. For example, cross-site scripting or injection flaws, which are one of the most serious web application vulnerabilities. So here is a short JavaScript example. This program assigns an HTML markup for a button to the DOM element innerHTML. Upon click, the button will invoke the function viewPerson on the input name, whose value is an untrusted variable. The code attempts to first sanitize the value of name. This is done via the closure library string function, HTML escape and escape string. Let's try to analyze whether the program works properly. First, we try to assign the string Tom and Jerry into name. It gives a desired HTML markup. But if we try to input the attack script, we get this HTML markup. The attacker script is executed after function viewPerson. This is a successful XSS attack. This is a subtle DOM-based XSS bug is due to calling the right except function, but in work order. So we need a tool to prove whether the program is safe. One option is convert the program to some string constraints, which is satisfiability if and only if the program will be vulnerable to attack. I'll describe a string language in which the string constraints can be expressed. A constraint is a Boolean combination of word equations whose right-hand side might contain the concatenation operator, regular constraints, and rational constraints. Circle is used to denote its concatenation operator. Rational constraints and regular language are represented as transducer and automata, respectively. Transducer is basically automaton with more tracks. Here is an example of transducer which has 2 tracks. Now I show you how previous snippet code can be transformed to string constraints. First, we can represent the implicit browser transduction as error-free. Next, we can express the right-hand side of the assignment to innerHTML as concatenation. The HTML escape and escape string function can be represented as R1 and R2. To simplify the security vulnerability, we provide an attack pattern for the variable innerHTML. We need a decidable fragment of the logic which mixes concatenation, regular constraints, and rational constraints, because the string language which was defined is a general undecidable. Fortunately, there is such a fragment which is called straight line, which we have already seen before. It was proposed in Linden Barcelona. Straight line conjunction correspond to sequence of program assignments in the single static form. A string conjunction is formula where by Psi is conjunction of regular constraints. Pi can be either rational constraints or concatenation, and each variable must be defined only once. The fragment of straight line conjunction can be straightforwardly extended to disjunctive formula. We say that a string formula is straight line if every clause in its DNF is straight line. So here is a formula from the previous example. And we check whether the given formula can be transformed into a straight line. But before that, we first rewrite the formula into different notation. This notation is quite natural since R2 can be viewed as string transformation from input x to output y. Now we can transform the formula into SL form. Now, this definition of straight line really corresponds to sequences of program assignments. As we can see, constraints are ordered according to program order. Each variable is defined before it is used, and each variable defined only one. There is an algorithm which was proposed in Lin and Barcelona. This algorithm can decide whether the formula is satisfiable or not. This algorithm first transforms the formula to NFAs, where concatenation is the most demanding operation. The resulting NFA is solved by algorithm which utilizes a which trick. It's a complexity theoretic algorithm which is hardly efficiently implementable. The contribution of our work is that we are able to solve the satisfiability problem of the formula X efficiently. First, we transfer the formula to one alternating transducer where each operation has linear size blow up. Then we transform the transducers to Boolean transition system with linear complexity, and then we will use some model checker such as IC3 or PDR. All transformation operation will be explained later. FAF, as well as the standard NFA, has set of states and set of transition. Like NFA, it also has existential branching. That is, when we are in state Q4, we can check to continue reading the words from state Q5 or state Q6. Additionally, the alternating automaton has also a universal branching, which works as follows. When we are in state Q1, then we have to be able to continue reading the word from both states Q2 and Q3. The main advantage compared to NFA is that alternating automaton can easily encode concatenation and all Boolean operation on formulae. Unlike standard definition of alternating automaton, we do not have just a single initial state and single set of acceptance state, but we use initial and final formulae. This approach allows us to easily translate the considered formula into alternating automatons in an inductive way. Now, in the following slides, I'll describe how to build a transducer from a formula. As the base case, we get rational constraints which are already represented as transducers, and regular constraints already represented by automaton. For example, rational constraints R1 is represented by transducer R1. Rational constraints R3 is represented by transducer R3, and so on. The translation into and transducer will be carried out in the following few steps. The first step might be transition of conjunction of two transducers. The conjunction of two transducers is translated to one transducer as follows. We take this union of their states and transitions. We take the union of the state and transition, and the initial and final conditions are simply conjunction of the original ones. Sometimes we need to deal with synchronization on the shared stack, which is described in more detail in our paper. So we already know how to translate conjunction to transducers, and the second step is how to translate concatenation to transducers. This step is divided into sub-steps. The first sub-step is to eliminate equation by substitution. We can see the formula, which contains only one concatenation, whose left-hand side, Z, is located in constraints R3. We replace every occurrences of variable Z by concatenation. Therefore, we replace the variable Z only in the rational constraints R3. The substitution preserves the straight line fragment. After substitution, we get following formula where the concatenation is already in the constraint R3. After substitution, we get the formula which contains only rational constraints. Now the constraints has one argument, which is concatenation, which leads us to a second substate. How can one handle splitting of arguments? Okay, let us consider a formula that contains one rational constraint R and one run of the transducer R. We need to split the variable in, Z into two parts, where each part of the variable Z always correspond to one of the variables x and y. After split Z into two parts, we get a new fresh variable Z1 and Z2, where Z1 is in relation to x and Z2 is in relation to y. A simple way of splitting Z into two parts is this. We make one conjunction of two copies transducer R for each possible configuration where the run of the original transducer may be split. This would generate exponentially many conjunctions, which we can do better with alternation. Instead of creating exponentially many transducers, we create only one transducer, which is the conjunction of two copies of the original transducer. At the beginning, we guess the initial configuration non-deterministically. Then we'll save the configuration by using additional states, and at the end of the run, we check whether the final states of left transducer correspond to the initial states of the right transducers. Initial is possible via generalized, final, and initial formula. Now, a simple transformation, some transistors into Boolean transition system is quite straightforward. States of the automaton become a Boolean variable of the Boolean transition system. The initial states of the systems is described by the same positive Boolean formula as in automaton, and the same for the final states in the systems. And the transition function of the Boolean transition system is conjunction of formula derived from individual transitions of the transducers. So the most important phase, please let it work. And the idea has been implemented to the solver slough, which read input formula in the SMT format. We have 4 sets of benchmarks divided into 2 categories. The first category contains 2 sets of benchmarks, which are based on a real JavaScript and PHP examples, and contain complex combination of transducers and concatenations. These benchmarks can be solved only our tool. The second category contains 2 sets of benchmarks. Both sets are from slog and contain simple combination of replace and concatenation. These benchmarks can be solved besides our tool, also CVC4 and S3P. And I think that's all, so thank you for your attention.
Any questions?
I hope not.
The internet was a little bit quieter. I think, getting close to lunch before hungry. So this is publicly available. Do you have any client, tools that are built on top of your solver yet?
No, I think so. Oh, no.
Do you have any plans to build client tools that use your solver?
Oh, of course.
What are some targets, I guess, for security purposes or
Targets? Yeah,
sanitization?
the base is security.
Any other questions for our speaker? All right, in that case, let's go to lunch. Thank you.